Hello and welcome to my capstone research project presentation, Plan First, Solve Later, Executor Aware MCTS for LLM problem solving. My name is Luke Winter. I am a student at CSUMB and my advisor for this project was Dr. Glenn Bruns. Let me start with the problem description. Imagine you want to use an LLM to solve some kind of problem for you. One way of doing this is just ask the LLM. It will give you a solution which may or may not be good. And the question is, can we improve this process without improving the underlying LLM? And it turns out you can do this. There are various techniques. One is to just ask the LLM to plan a little bit before giving you an output. And these all fall under the umbrella of reasoning or inference scaling. One general problem these techniques have is that they often struggle if the required reasoning is too long or needs too much creativity. And also the space of solutions which we're trying to explore, which may, for example, in competitive programming, be the set of all programs that could solve this question, is very big and inefficient to search. And some naive ways of scaling this process, like for example just asking the LLM over and over again to give you a solution, are often naive, which is where the Executor Aware MCTS comes in, the technique that we're proposing. Note that there are many other techniques that have been proposed in the past. This builds on this prior work, but to give you a high-level overview, this technique sits as a layer between the prompter or problem asker and the LLM, and this layer will then iteratively ask the LLM to plan a little bit and then implement some more and then plan some more and then implement again. And this whole process is guided by a reward model which can take a solution, test it, and then assign a score to the solution, which is used to steer the search. Before I go into more detail, let me talk about the algorithm changes we went through over the last months. At first, the idea was to create many plans independently. Now these plans are being created jointly, such that new plans may build off of and improve on old plans, hopefully making the whole process more efficient. And at first, the idea was to have MCTS search through implementations or solutions. Now MCTS is used to search for an optimal plan. This is a sort of a shift in perspective. So let me go into more detail for the algorithm. At the core of it is the plan tree, in which each node is a plan step. For example, we tested the algorithm on competitive programming problems. So an example plan step might be initialize a hash table or iterate through the string and count character occurrences. And each plan node or plan step has a corresponding implementation in code. So on the right, you can see a diagram. Plan 2 is a plan step that logically follows the plan step plan 1. And each has a corresponding implementation. So how do we search and expand this tree? We start at the root node and then we traverse to one of the children. Say we traverse to plan 3. Then we traverse to one of the children again, say plan 4, it's the only one. And at this point, the plan may or may not be complete. If it is not complete, then we expand the tree with more nodes. And then when the plan is complete, we also have a solution ready by concatenating these code implementations, which we can then test and assess. And the score assigned will be used to update some statistics about these nodes. The crux is that these statistics will then be used to guide future traversals through the tree, such that we're more likely to traverse promising nodes and expand those as opposed to unpromising nodes. Let's talk about the results. Unfortunately, at this point, the results are still suboptimal. We tested the algorithm on 50 competitive programming problems from the Code Contests benchmark. And we tested it against two other techniques. One is an ablation, which is very similar to our algorithm, with the only difference being that each node has at most one child, which turns this essentially into a linked list where we have a plan and then an implementation, and that's it. And then a naive technique where we independently, iteratively ask the LLM to give you another solution for the problem. So one solution, another, and then we just keep the best solution. On the left, we see the fraction of problems solved, and the MCTS underperforms the naive with 40% pass rate, whereas the naive has 52% pass rate. And on the right, we have a diagram that shows how well these algorithms scale as they're given more time to search for an optimal solution. On the x-axis is the total tokens used, which is a proxy for how much time was spent, how much compute was spent on the search, because the LLM token output production is the bottleneck of the whole thing. And on the y-axis is the average score across all 50 problems obtained as the fraction of test cases passed, plus some bonus for efficient solutions. A score of 2 is perfect. And we can see that naive and MCTS algorithms both scale similar. The shape is similar, although the MCTS underperforms the naive, flattening out at around a score of 1, although more testing is necessary and we're going to try and improve this algorithm further. Now, as for my learning, I definitely learned a lot from this whole project. First of all, I learned a lot about the research behind reasoning, LLM reasoning and inference scaling, about the different kinds of techniques that are out there. I also learned how challenging it can be to work with LLMs because of their stochastic nature. Sometimes they just don't behave as you would expect, which makes parsing their output very challenging. And I learned how difficult it is to implement MCTS from scratch. Let me end on a big thank you to my mentor, Dr. Glenn Bruns, who was immensely helpful throughout the entire project. And also a big thank you to you for listening. I hope this was interesting. And here are my sources. Thank you.